So next we're going to discuss what's called the second derivative test. And we'll start by identifying when we would want to use the second derivative test. And that's what this first sentence will tell us. So the second derivative test allows us to avoid using the first derivative table. So what do I mean by avoiding using the first derivative table? Well, remember, when we got up to the point in the second problem where we identified our critical number of x equals 600, how did we actually determine that this was the location of a local maximum? Well, we drew our first derivative table, we plugged in a sample point to the left of 600, and we plugged in a sample point to the right of 600, and we determined that the function actually changes from increasing to decreasing at the point 600. And it was actually the first derivative test that allows us to jump to the conclusion now that based on our analysis in this table, we can conclude that x equals 600 is the location of a local maximum. That's the first derivative test that allows us to do that. Now, what the second derivative test allows us to do is avoid drawing this table. Okay, and under certain circumstances. It doesn't always work, but sometimes it will allow you to avoid using that table. And here's a statement of the test, and it tells you, well, pretty much tells you exactly when you're going to be able to do that. So when f double prime, well, pardon me, it tells you when you're going to be able to do that, and by do that I mean avoid drawing the first derivative table. It tells you when you'll be able to do that and how you'll be able to do that. Okay, so the first thing is when you'll be able to do that. So the assumption for this test is that you've got a function f whose second derivative is continuous near the point x equals c. There's that word near again. Remember what that means? If I am assuming that f double prime is continuous near the point x equals c, then what I'm really saying is the following. Let's just imagine what the number line might look like. You got a point c on the number line, right? And the idea is no matter how wonky the function might be some positive distance away from C, as long as it's possible to draw some window around the point C, which might have to be really narrow. I might have to really zoom in order to be able to construct a window like this, but it's going to have the property that over that entire interval, f double prime is continuous. Right? That's what we're really assuming when we say that we assume that f double prime is continuous near some point x equals c. It means you can do this. It means you can choose a window around the point c that's narrow enough to make this work. Okay, well, let's say you've got that assumption laid out. What does the second derivative test tell you? Well, it says two statements. The first one says that if f prime of c is equal to 0 and, so this first part really you're saying if c is a type 1 critical number of the function f, because that's really what it means for f prime of c to be 0. And if you plug that point c into f double prime and you get a positive number, that's what this really represents, that's what this is saying, well then you can conclude that c is actually the location of a local minimum. Now let's look at why that's the case. So forget about the second statement for the moment. Let's just draw a picture of why we get the first statement. Think about it this way. Think about it. What would a local minimum look like? Well, a local minimum, if you're looking for local minimums, you're going to look for stuff like this, right? This is kind of what you should have in mind when you imagine a local minimum of a function. They don't all look exactly like that, of course, but that's kind of the idea or the picture that's useful to have in mind when you're thinking about local minimums. And then local maximums are going to kind of look like this. Right, so local minimums happen when there's a valley, and local maximums happen where there's a hill or a mountain, right? And so the local maximum would be right up here, and the local minimum would be down here in this function. So, and notice, what's the concavity of this graph here? Is it concave up or concave down? It's concave up, right? Because if I poured water inside, the graph would catch the water, in a sense. So that's why this graph is concave up. And so if you have a type 1 critical number and the function's second derivative is continuous near that point, then you know that you have a local minimum. Because this is really what you're checking for. That's why you plug the point c into the second derivative. If you get a positive number, what that's really showing is that near the point c, at least close to that point c, the function's concave up. Okay, so that's really what you have here. So you've got, I'll just finish the graph here. So you've got some point c, f double prime of c is greater than 0. I won't draw the y-axis here because it just kind of gets in the way. And really what you get from that is you get a local minimum. Okay, and then we can do kind of the same investigation in the case of a local maximum. If you have a local maximum at some point C, well, what's the concavity of this graph? Well, if I poured water on top of this graph, the water would run off the sides, right? It's concave down. That's the concavity is in the downward direction. So this graph is concave down. So this is the picture that you should have in mind when you read the second statement. So if you've got a critical number, a type 1 critical number C of the function f, so in other words, if f prime of C is equal to 0, and furthermore, if you take that number C and you plug it into the second derivative and you get a negative number, well, that really is telling you that at least if you're close to the number C, if you stay close to the number C and take some narrow interval around the point C, the function is going to be concave down on that interval, at least if you're close to C, right? If you move farther away from C, that may no longer be the case, but at least close to C, you've got a downward concavity, like in this picture. So what does that give you? Well, that gives you a local maximum, as you can see in the picture. These are the pictures that you should have in mind when you think of the second derivative test. So local maximums happen where the function's concave down, and local minimums happen where the function's concave up. Now, again, that's not always the case, right? You could have a local maximum that appears where the function's not concave down, but not if your second derivative is continuous near C. So that's the importance of this assumption here. So let me actually draw you a picture of when this could fail. And I don't mean the second derivative test would fail, but what I mean is the statement that local maximums, if I try to go further with this and say that, well, local maximums are always going to happen when a function's concave down, well, that would be going too far, right? And I'm going to show you an example of why that's the case now. Well, think about this one. Maybe I have a graph like that. That's not concave down. In fact, if anything, it's concave up, although there's an issue with the concavity right at that point, right? Or right at the x value of that point, whatever it is, it's not concave up, or it's not concave up at that point, because I would say it's not even differentiable there. So it's definitely not second differentiable at the x value of this point, whatever that may be. But it's definitely not concave down, right? But that is a local maximum. So let's make that observation. This is a local maximum, but the graph is not concave down. So the reason that that's not a violation of the second derivative test is because the graph of this function does not have the property that if you call this some function f, let's say, let me do that now. Let's call this function f. So y equals f of x. And we can even go further to say that the x coordinate of this point, let's call that c. In this case, f, this is not a let me put it in this way. I'll stretch this down to give myself a little bit more room. So this is not a contradiction. So I'll say this is not in violation of the second derivative test. And why is that? Because the second derivative of the function f is not continuous near C. In fact, it's not even defined at C. So f double prime is not continuous near C. Okay, so just about had issues squeezing that in there, but we did manage to fit it in. That's the idea. So this is not an absolute. This is not going to capture all of the situations that you might deal with. However, it is going to capture most of the situations we deal with. So most of the time we don't deal with functions like this, but they could arise. So I did want to include this example just to show you why the first derivative test is not something that you can completely do away with, right? It's still important, but quite often the second derivative test will give us a shortcut that we can use. And I'm going to show you how to use that in the next example. And it's going to turn out to be quite a useful shortcut. It's going to save us quite a bit of effort in this example. So here it is. We got a cylindrical can that we want to build, and it's supposed to contain 1,000 cubic centimeters of oil. And well, what we're asked to do is find the radius of this can that's going to make it as cheap as possible. Or in other words, is going to minimize the amount of surface area that the can has, right? Because the surface area really translates to the amount of materials that you're going to need to build the can, right? A can with a large volume but a low surface area is cheap to make but practical because it has a high volume. Whereas if you have a can that's got a very low volume but a high surface area, that's going to be less practical because it contains less fluids, but it costs more money to build. It takes more materials to build, and materials are really synonymous with money in this case. Okay, so that's what we want to do. We want to figure out what the radius of the can would have to be in order to minimize its surface area. So what does that mean? Let's start with a picture. Let's draw a cylinder, right? Start by drawing the cylinder, and then everything else is easier to go with after that. So let's start by drawing a picture of our can. So cylinders look like this, right? They've got a circle on top, circle on the bottom, and then that's roughly the shape of a cylinder, right? So what's the radius? Radius means the radius of a cylinder is the radius of the circle at the top of the cylinder. Right? Cylinders have circles built into them. So the radius of that circle, that's what we mean when we say the radius of the radius that minimizes the surface area of the can. We're talking about the radius of this cylindrical can. This is the radius we're talking about. So let's say R is the radius of the can. So I'll say radius of the can. And what units are we going to use? We don't need to set anything in stone, but I mean, it seems like centimeters would be the one to use, right? If this volume is measured in centimeters cubed, it's going to make sense to measure one-dimensional distances in centimeters. So let's say in centimeters. And the other attribute of the cylinder that's going to matter, the one that's going to play a role in volume and surface area, which are built into this question, right? We've got volume mentioned and we've got surface area mentioned. So we're going to need to work with formulas for those quantities, and they involve the radius of the cylinder, but also the height. So the height of that cylinder is also going to matter. So let's say that H is the height of the can, and we'll measure that in centimeters also. All right, and let's mention this just like we did last time. Let's mention that we need both of these quantities to be positive. Right, we need the radius and the height both to be greater than 0. Okay, because again, if you try to imagine this radius shrinking and shrinking and shrinking and then going down to 0. If the radius was 0, you don't have a can anymore. It's not going to hold any volume. And if the radius is negative, well, then I don't know how you would even want to think about that. But you probably can imagine it's going to not give you a practical can, right? If you imagine the radius going negative, maybe you've got a can that's inside out in some other dimension that you can't even access anymore. If you are entertained by those kind of thoughts, go ahead, but it's not going to be a practical solution to this problem, right? So we need to restrict ourselves to the case where the radius and the height of this cylinder are both positive. And it saves you some time later to actually take the time to make that observation and set it in stone now, because remember, you might find more than one critical number. It's nice if you can throw a bunch of them away because they happen to be negative, right, when you were doing these problems. So take the time to make this observation early on. Okay, volume and surface area are also mentioned, so let's fill that in. So V, the volume of a cylinder. How do you measure the volume of a cylinder? Just take the area of that circle and multiply it by the height. So the area of that circle on top is going to be pi r squared. And if you multiply it by the height of the cylinder, you're going to get pi r squared times h. So that is going to be the volume. So let's mention that. And then also surface area. What's the surface area of a cylinder? Well, for starters, you have the top, right? You can measure the area of the top face of the cylinder. That's going to be pi r squared. For the, let's use A for the area. So area, we're going to have pi r squared for the top face of that can. But there's also a face on the bottom that's going to be another circle, right? So there's two circles to take into account. So let's start with that. 2 times pi r squared. Okay, and how do you get the rest? What about all this area around the side that you have to wrap around those circles to actually make it into a can? And it may help to actually think of it this way. This is how I like to think about it. Imagine you took an X-Acto knife and you just made a cut down the side of that can. And then you just peeled this out that way, and you peeled that side out the other way, and you flattened it out until it was a rectangle. So imagine that. If you had this as a rectangle, okay, I'm drawing it small so I can fit here. So you imagine you made that cut and then flattened out the cylinder so it was a flat rectangle. Well, what would this distance here be? Well, it would still be the height, right? If I took this and I peeled it outward into this rectangle, this would be the height, right there. What about the top distance? What about this distance? What would it be? Well, it would be whatever the distance is around this circle, starting from this point, going all the way around to back where you started with. That's what the top side would be, right? The width of this rectangle, or the base. Well, that's the circumference of this circle, which is just 2 pi times the radius. So that top side is going to be 2 times pi times r. So really, that's how you can finish off the formula for the surface area of the can. You're going to have to add up those two circles, right? The top, the bottom, but then to get the side, you can multiply h times 2 pi r. So you'll have 2 pi r squared plus 2 pi r h, and that is going to be your surface area. Okay, so that is our formula for volume and surface area, and from here we can actually now turn this into an optimization problem, and that'll be, we'll just have room for that on this page, and then that'll pretty much use up all of our room. So what are we trying to optimize here? We're trying to optimize the surface area in the sense that we want to make it as small as possible, right? It says find the radius that minimizes the surface area of the can. Okay, so let's start with that. We want to minimize A, which is equal to 2 pi r squared plus 2 pi rh. And we want to minimize that subject to the following constraint. What's the constraint that we have to worry about? Well, it's given in the first sentence of the problem, right? A cylindrical can is to be made to contain 1,000 cubic centimeters of oil. So it has to contain 1,000 cubic centimeters of oil. That means the volume of this can has to be 1,000. So subject to volume is equal to 1,000, right? Really what we're going to do is that's going to force pi r squared times h to be equal to 1,000, which is going to give us a relationship between r and h, and that's what's going to allow us to reduce A, the area, to be a function of a single variable, and that's what's going to allow us to actually solve this problem. So that's just roughly how this is going to go. We'll work out the details on the next page, but this is our optimization problem that we're going to solve now.